All right, good afternoon, everyone. For today, we are going to start chapter 3, integration. So let's talk about the concept of antiderivative and indefinite integral first for today. And then next week, next Monday, we are going to start talking about the definite integrals and how it related to computing the area. All right, I know that some of you have seen integration before and it was a nightmare for someone. So we're gonna start from the basic and just keep going. And then we're gonna talk more and more and more about integration after midterm. All right, so first let's look at the definition of antiderivative. So I am going to look at the motivation first. So let's suppose that you have a function f. As I show you on the slide here, I have function f equal to x cubed. If I take derivative of f prime x, so I'm gonna get 3x squared, right? Because I just differentiate one time. If I differentiate x cubed plus pi, so this thing I am going to get 3x squared as well. And also x cubed minus 5, if I take derivative, so I am going to get 3x squared as well. So for any constant that I add here, so it doesn't matter with my derivatives. So it's gonna get, I am going to get 3x squared anyway. So the same thing with the function sine. So let's say that I have sine x, and then if I take derivative of sine, I get cosine. If I take derivative of sine x plus 4, I get cosine x. I take derivative of 4, I get 0. So that means I still have cosine x here. And then you can see that the same pattern happens here. So if I take derivative function f with respect to x, where f is sine x plus some constant, so I will get cosine x anyway. So that means we observe that if you have x cubed plus c, so when you take derivative with respect to x, so you get 3x squared. And then if you take derivative of sine x plus c, so you get cosine x. So this is how derivative works. But let's suppose that you have things on the right hand side. Suppose that you have 3x squared or you have cosine x, and you want to find a function that once you differentiate it, it gets back to 3x squared. So that function is called antiderivative. Well, the idea of antiderivative is you trying to reverse the operation of derivatives. So let's look at the definition here. So I have a function f. So a function f is an antiderivative of f if you differentiate that function capital F and then you get back small f. So that means, yes, if you have 3x squared and you want to find the antiderivative of 3x squared, so you're going to have so many solutions. So one of them is x cubed minus 5. So another one could be x cubed plus 1, could be x cubed plus 1/3. And antiderivative of cosine x, it could be sine x plus 4 and could be sine x plus any constant. So with that concept, so we're gonna say that when you find the antiderivative of a function f, your answer gonna be in the form the capital F plus c. So you have to add constant into your answer all the time, because you know that if you differentiate constant, you get 0. So that means when you compute antiderivative, it means, well, you have to add c back into your answer. All right, so that's called antiderivative. So I'm gonna go over our theoretical part first, and then we're gonna do the examples after. So the next thing that I am going to show you is the definition of indefinite integrals. So for the indefinite integrals, we are going to give a notation, a proper notation for antiderivative. So once you compute your antiderivative of f, so we're gonna give it a notation, this integral sign of fx dx. Well, I know that you have seen this sign before. This sign is called an integral sign. And by definition, we're gonna define this integral sign of function f to be antiderivative of f. So, which means if I give you a function small f here, you can find a capital F, which is your antiderivative of small f, and then you have to add c because when you take derivative of constant, so you're gonna get 0. The thing that is inside the integral sign here, you're gonna call it integrand. And then your x here, this is going to be your variable of integration. Sometimes it's gonna call dummy variable. So the idea is we're gonna define our antiderivative to be a function. We are going to define our antiderivative to be a notation integral sign of f dx. All right. So let's look at the basic rules of integration. So how do you find the antiderivative or indefinite integrals? So the first rule that you can use is the constant rule. So because you know that when you differentiate kx, you're gonna get back k, right? That means when you take the antiderivative of k, so you're gonna get back kx plus c. So that means your integral of k dx, you're gonna get back kx plus c. So the next thing is the constant multiple rule. So when you have integral of k fx dx, so you can pull out your constant k outside the integral sign. So you can pull out your constant k outside the integral sign. So dx here as well. And then rule number 3, sum and difference rule. So when you have integral sign of sum or difference of two functions, you can split it as shown in rule number 3 here. So those are basics rule of integration, and we're gonna use it all the time without any doubt. So you can, well, I think this is the basic one, and you shouldn't have a hard time to memorize this thing. So for example, let's look at integrate 3dx here. So what I'm gonna get 3x plus c, right? Because I know that if I differentiate 3x plus c, so I'm gonna get back 3. So if I differentiate square root 2, so I'm gonna get back square root 2x plus c. If I integrate negative pi dx, so I'm gonna get negative pi x plus c. Simple like that. So the same thing with when I have constant time the function f. If I want to integrate 3 times fx dx, I don't have to be worried about number 3 here. So I can pull out number 3 here. So I get 3 times integrate fx dx like that. Well, that is how constant rule, constant multiple rule, and the sum of difference rule work. So we're gonna take more step into the power rule. So this is the important one that you're gonna use it all the time. So if you consider when you differentiate x to the n plus 1 here, so you're gonna get n plus 1 x to the n. So if you divided everything by n plus 1, so you're gonna get that if you differentiate x to the n plus 1 over n plus 1 here, so you get back x to the n. Keep in mind that here n is not equal to negative 1 because you divided everything by n plus 1. So if n equal to negative 1, your denominator is going to be 0 and it is undefined. So n cannot be negative 1. But any other value of n, so you can obtain this formula. And if you think of this formula of derivative of x to the n plus 1 in terms of integration, so that means if you integrate x to the n, so you're gonna get back the function that I highlight in light blue plus some constancy, right? So for example, if I want to integrate 6x squared, so here I can pull out number 6. So I have 6 times integrate x squared dx. And then after that, I integrate x squared dx. So I get x cubed over 3, right? And then plus c. So you can memorize that when you integrate x to the n. So you're going to get x to the n plus 1 over n plus 1. So the power gonna add up by 1. So if you want to integrate 1 over square root x dx, here this is integrate x to the negative 1/2, right? dx. So when you integrate it, I would recommend you to switch your square root x to x to the negative 1/2 first, so you can see it easily. And then now you can integrate that. So it's gonna be x to the negative 1/2 plus 1 because you need to add 1. And then over negative 1/2 plus 1. And then plus c. So if you simplify that thing, so it's gonna be x to the negative 1/2. X to the 1/2 because that will be positive now, and then over 1/2 plus c. So if you want to simplify more, this is going to be 2 times square root x plus c. Well, every time when you compute integral, you can check your answer. If you want to check your answer, you can differentiate your answer, and then it's going to get back to what is given in the problems. All right, I hope power rule is not too hard for you. So I know this is a basic from high school, but today we need to give you a review first, and then we can take more steps to something more complicated. All right, so the last rule that we obtained from the previous chapter. So because we know the rules for differentiate trigonometric functions and inverse trigonometric functions, so we're gonna get back some set of integration rules. So the first one is trigonometric rule. So because you know that differentiate sine, you get cosine. So that means integrate cosine, you're gonna get back sine. Well, because you know that differentiate cosine, so you get negative sine. That means if you integrate sine, so you're gonna get negative cosine. Does it make sense? Because you know that differentiate tan, you get secant square. So that means if you integrate secant square, so you're gonna get back tan. So because you know that uh, differentiate cotangent, so you're gonna get negative cosec square. So it means if you integrate cosec square, so you're gonna get back negative cot. So those 6 formula, we got it because we have differentiation rules. So when you reverse it back, so you get 6 formula for free. So the same thing with inverse trigonometric functions, because you know that arc sine, if you differentiate arc sine, so you get 1 over square root 1 minus x squared. So that means if you integrate it, so you get back arc sine. And also integrate 1 over 1 plus x squared, this is arctan. And also if you integrate 1 over x over 1 over x times square root x squared minus 1, so you get arcsec. So you have no choice, you have to memorize this thing. You have to memorize this set of formulas. no choice. So you have to memorize it. So today is the first day that you memorize the formula. So it's going to be hard for you to memorize it all. But eventually, I hope that after 2 or 3 weeks, so you will memorize it all. All right. So I mean, the only way that you can memorize it, you have to use it again and again and again and again until you absorb it. Does it make sense? So I have talked a lot about the rule of integration. So for the next half an hour or 40 minutes, we are going to go over some examples to show you how it's work when you face the problem. So before we get started, any question? So if you don't have any question, for those of you who are in today, about 40 students, so you can type check in on the chat. So I know that you check in today. So we are going to start example now. All right. So I think today we have so many examples. Let's see. Well, we have some example that is interesting for today. So let's get started. All right. So everyone type check in, no question. All right. So we are going to start by looking at example 57. All right, this is the easy one. So 57.1, I want to integrate x cubed plus 2 sine x dx. So simple. Well, if I want to differentiate, if I want to integrate x cubed, so that means I have x to the fourth power over 4, right? Because it's in the form x to the n. So I can add the power by 1. And then if I want to integrate 2 times sine x, so I don't have to integrate 2 because this is my constant. So I can pull out from my integration. I mean, pull out of the integral sign. And then what I have left, I have sine x. So I have to integrate sine. So what is the formula for integrate sine x? So we have negative cosine x, right, plus c. So, and that will be my answer, x to the fourth power plus 4 minus 2 cosine x plus c. Well, this is the easy one. So keep in mind that if you cannot memorize the formula of integration, think of differentiation first. Well, differentiate cosine, you get negative sine. That means integrate sine, so you get back negative cosine. All right, so let's take more step by looking at this example 57.2. So I have integrate x squared cosine x plus x squared minus 1 square over x squared. Here what I'm gonna do, well, because the function on the numerator is so messy, so I'm gonna split it into 2 pieces. Why is that? Because I see that I have x squared here, I want to cancel. So I'm gonna split it into 2 pieces first. So I have integrate x squared cosine x over x squared dx, right? And then plus integrate x squared minus 1 square over x squared dx. Well, I can split it into 2 pieces because the sum and difference rule of integration. And then after that, I can cancel x squared. So the first term gonna have just cosine x. So, and the second term, I am going to expand my numerator here. So I expand my numerator, so I get x to the fourth power, and then minus 2 times x squared, and then plus 1, right, over x squared dx. So I am going to simplify the second term first. So if I simplify it, so I cancel my x squared with the term on the numerator. So I have x squared minus 2 plus 1 over x squared. So now I'm ready to integrate. So I'm going to integrate cosine. Now I get sine because I know differentiate sine, I get cosine, right? And then I I integrate x squared. So I get x cubed over 3. I integrate negative 2. So I get negative 2x. And then I integrate 1 over x squared. So if you have a hard time to integrate this thing, so think 1 over x squared dx. So to integrate this thing, you better, for those of you who are beginners, so you should start from integrate x to the negative 2 first. Just go slow. Nothing wrong if you go slow. So this is going to be x to the negative 2 plus 1 over negative 2 plus 1 plus c, right? And that will be x to the negative 1 over negative 1 plus c. And that will be negative 1 over x plus c. Wow, slow but sure. So now you get negative 1 over x, and then you plus c at the end. Does it make sense? Well, I'm going to make this thing cleaner. All right. All right, that is how you integrate these problems. So actually, when you integrate each term, you're going to have plus c for each term. But because those are constant, you can just sum it up and write plus c at the end only one time. Right? All right. Any questions so far? So this is a simple question. Example 57. If it show up on the exam, this is considered as an easy question. Everyone should be able to do it. If you skip this question, well, that means you skip easy question, and that will be your, I think that it will be hard for you to pass this class if you cannot solve like those easy questions. All right, so we're gonna move to example 58. All right, so let's look at something more challenge. So I have integrate 1 minus x squared over 1 plus x squared dx. So here, how do you integrate this thing? So if you memorize the previous slide, I have one set of formula that I have the inverse of the inverse trigonometric rule, and then you can see that what I have this formula: integrate 1 over 1 plus x squared equal to arctan x, and also I have 1 over square root 1 minus x squared equal to arc psi. We're going to use these two formula again and again, so memorize it. By this I mean when you see the integrand that contains 1 over 1 plus x squared, you expected, your expectation is the answer can be arctan. So for this question, if you see that, well, you have 1 plus x squared in the denominator. So what you can do is, well, if you think, pretty simple, 1 over 1 plus x squared gx, right? You split it and then negative integrate x squared over 1 plus x squared dx. Is that better? The answer is yes, because at least you know that you can integrate this thing, right? Because this thing gonna come back to arctan x because we have the formula for that. However, this term you still have a hard time with it, right? Because how do I integrate x squared over 1 plus x squared? So for sure, x squared over 1 plus x squared, you cannot split it into this thing. No, for those of you who are weak in algebra, no, you cannot do this. This is unacceptable for simplify the terms, right? So what we can do, this is a trick. So we are going to do some trick here. So the thing that I'm gonna show you here, so I'm gonna simplify something on the top a little bit. So I'm gonna say that, hey, my given problem, this is integrate 2 minus 1 plus x squared over 1 plus x squared. So the reason why I do this because, well, I want to see 1 plus x squared here. Because if I see 1 plus x squared here, so once I split it, it's going to cancel with the thing in the denominator. So I get constant and it can be integrated easily, right? So if I want to see 1 plus x squared, so I need number 2 here to balance it. So basically, I just simplify my 1 minus x squared to 2 minus parenthesis 1 plus x squared. So once I simplify something like this, so I can split it into 2 over 1 plus x squared dx. And then the second term gonna be negative integrate 1 plus x squared over 1 plus x squared dx. And that would be 2 times integrate 1 over 1 plus x squared dx. And then that would be integrate 1 dx. And then now, so you can integrate, that will be 2 times arctan x. And then minus x plus c. So this will be your answer. You can double check by if you integrate, if you differentiate the answer in the box, so you get back to the term that I have in the question. So you're gonna have a question that, Ajahn, how do I know this thing? How do I know this technique? Well, the answer is your experience. Well, when I see the problem, I can deal with it easily because I have seen it more than 1,000 times, right? Because I mean, I have experience with integration. So I know that for this type of problem, I want to do this, I want to do this. Well, in the book, there's no book for you to just summarize it for you that, hey, when you see this, you have to do this. When you see this, you have to do this. It based on your experience. If you do exercise more, you're going to have more experience. You're going to sharpen your skill. And then once you do more example and more problems, so you will find that you are more comfortable with integration. Any question on 58.1? You still hear me, right? So most of my internet connection is not that stable, but hopefully you will understand this example. So it is not that hard, but the hardest part is that it is tricky. Is it tricky? So the next thing, example 58.2. So we want to integrate tan x minus secant x squared. So here, so I'm going to copy the question first. So how do I integrate this thing? So first of all, I look at my tan x minus secant x. Is it good if I expand this thing? Well, I look back at my formula first. Well, what I have integrate secant square x, right? Well, it means if I expand tan x minus secant square minus secant x square. So if I expand it, so I am going to see tangent square and secant square. And secant square, good, I have a formula. And also the middle term after you expand, so you're gonna get secant and tangent multiplied together, which you know how to differentiate, how to integrate as well, right? Because integrate secant and tangent, you get secant. So for this reason, I am going to expand it. So I am going to expand this thing, so I get tan square x minus 2 times tan x secant x, and then plus secant square x dx. Well, after I expand this thing, so I'm gonna split it into 3 pieces. So the first one is integrate tan square x minus 2 times integrate secant tangent, right? And then I am going to have plus secant square x dx. Well, this term is easy. We have the formula. This term is easy. We have the formula, right? Because we know that integrate secant, you're gonna get integrate secant square, you're gonna get back to tan. Integrate secant and tangent, multiply together, you're gonna get back to secant. So how do you deal with integrate tan square x? You don't have the formula for it, right? So for now, you don't know the function that you differentiate, and then you get back tan square. So how do you integrate tangent square x dx? So any idea? So in the chat, can you type? Any idea how can I integrate tan square x dx? Well, Shawin say, can we simplify tangent to sine over cosine? Napatra say identity. So I know that trigonometric identities are hard, but well, sometimes we have to use trigonometric identity to simplify some trigonometric term, and then that will leave something that we can integrate easily. So to deal with tan square x, so thank you Napatra and Choin. So you were brave enough to answer me, and I appreciate it so much. So Napatra gave us the correct answer. So we are going to look at trigonometric identities to switch our tangent to secant. So let me give you a review. This is very important because, well, some of you forgot everything about trigonometric or trigonometric identities already. So let me give you a review. So when you learn trigonometric identity from high school, so you have learned so many formulas, but my trick is that you only need to memorize the basic formula and then you go from there. So the basic identities for trigonometry is sine square x plus cosine square x equal to 1. I call this thing the mother formula because this is the key point for everything. Every identities in trigonometry start from this formula. So this is what you have to memorize. So if you memorize sine square x plus cosine square x equal to 1, you're gonna get two formula for free. So another two formula that you're gonna get from this identity for free is if you divided everything, if we divided everything by sine square x, so what do you get? So if you divided everything by sine square x, so you're gonna get sine square x over sine square x plus cosine square x over sine square x, and then equal to 1 over sine square x here, and then that means you get 1 plus cotangent, right? And then this is going to be cosec square. So this formula you don't have to memorize, but every time when you want to use it, you can start from the key formula here, and then you divided everything by sine square. Well, it's give back you the formula you want. So the same thing if I divided everything by cosine. If you divided everything by cosine, see what you get. So if you divided everything by cosine square, so you're gonna get tan square x plus 1 equal to secant square x. This is the formula that you get it for free. Well, I don't know how you did trigonometry in high school, but if I have to teach you trigonometry, I'm not going to tell you memorize the formula. You have to memorize only the important formula, like, well, you just memorize sine square plus cosine square equal to 1. And then you're going to get two formula for free. So the thing that I'm going to use on this question is, because I know that tan square x equal to secant square minus 1, right? From here, I'm going to get tan square x equal to secant square x minus 1. So I know that. So I'm going to go back to my integration question and use it. So that means I'm going to replace my tan square. Well, my tan square going to be secant square x minus 1. All right. Better, right? Because I see secant square now, and then I'm happy now. So I want to simplify a little bit more so I can integrate. All right. The last two terms, I'm not going to touch it because I can integrate anyway. So I'm going to group secant square together. So I'm going to have 2 times integrate secant square x dx, and then minus 1 dx, and then minus 2 integrate secant x tan x dx, right? And then, whoa, integrate secant square, so you get tangent. So integrate 1, so you get x. Integrate secant tangent, so you get secant plus c. So this is your answer. How do you feel? Better? So you can see that integration is an art. Integration is an art. So it is not like differentiation. Differentiation, if you know formula, you can do it because it's going to be formula. Memorize the formula and do it. So differentiation is usually easier compared to integration. So integration, you only have the formula for some function. You can see that for integration, I don't have product rule. I don't have quotient rule. Well, you need to practice a lot to know the technique of integration. All right, so we have few more examples today. So we're gonna keep doing some examples. I think we can do maybe 5 or 6 more, and then that will be all for today for the time. All right, so let's move to another example here. So before we go to this example, so if I give you a function f prime and I ask you for the regular function f, you can do it by integration, right? Because you know that if you start from f prime and then you integrate, so it's gonna give you back your antiderivative. So that means this formula holds. So let's look at an example here. So suppose that I have f prime x equal to 8x plus psi x. This is the easy one. So I know that f prime x equal to 8x plus psi x. And then the question asks me for the function f. So I want to know what function f such that if I differentiate f, so I get back f prime. So for sure, my f is going to be integrate that function, that given function, right? And then if I integrate just 8x plus psi x dx, so I'm gonna get 8x squared over 2 integrate psi, you get negative cosine, and then do not forget to plus c. Well, the thing is that your c gonna be your arbitrary constant. However, sometimes the initial condition is given. So if the initial condition is given, you can solve for the value of c. So for this question, I give you an initial condition f pi over 2 equal to 2 pi. That means when x equal to pi over 2, y equal to 2 pi. So that means for the equation that you have, so you have y equal to 4x squared minus cosine x plus c. This is your equation, right? After you compute your antiderivative or indefinite integral. So this is your answer. And then now you know that, hey, when x equal to pi over 2, when x equal to pi over 2, so your y is equal to 2 pi. So when x equal to pi over 2, see, your y equal to 2 pi. So that means I can solve for c. So here I'm going to get pi square, right? So pi over 2 square. So I get pi square over 4. That is, I get pi square. And negative cosine pi over 2 is 0, right? And then that is minus 0 and then plus c. So that means, well, I can solve for c. c is going to be 2 pi minus pi square. So my complete answer is going to be fx equal to 4x squared minus cosine x plus 2 pi minus pi squared. Well, the reason why I show you this example because I want to show you that, well, you can solve for c if the initial condition is given. So we're going to learn this thing a lot in calculus 2 when we move to differential equations. So this thing is called initial condition. And when you model the real problems in engineering for now, so we are going to look at the last thing for today, the substitution rule. So let's look at the statement of the substitution rule. So the substitution rule say that, well, if you want to integrate, well, I look at the statement already. So if you want to integrate f of gx times g prime x dx, so you're going to get back integrate f u du, where u equal to gx. So this substitution rule going to help us a lot because most of the time we're going to have the integrand that is similar to the term on the left hand side. For example, if I have integrate, let's say that if I have integrate 2x cubed cosine x to the 4th power dx, and I want to integrate this thing. So you can see that we don't have the product rule for integration. We don't have the product rule for integration. So we cannot say this is integrate 2x cubed dx times integrate cosine x to the 4th power dx. If you do that, wrong. We don't have the product rule of integration, so you cannot do it. That is why integration is so hard, because you don't have product rule. And also, if you look at the equation that I have here, so I can change my variable from x to the 4th power to u. So if I let my u to be x to the 4th power, so what happened is I am going to simplify my thing to be integrate to x cubed cosine u, right? Because I just switch my x to the 4th power to u. And then once I have u here, so what does it mean if I change x to the 4th power to u? So how does my dx switch to? So let's think about the substitution here. So you have u equal to x to the 4th power. If you want to find du, So that is going to be, well, if you want to differentiate u with respect to x, so you get du by dx equal to 4x cubed, right? And if you write it in the differential form, this is going to be du equal to 4x squared, 4x cubed dx. This is in the differential form. Differential form, right? So that means, hey, if I have dx and I want to switch to du, you can view it as du over 4x cubed, right? Does it make sense? Because you can view that thing in the differential form, and then you can view dx, my dx, as du over 4x cubed. And you know what? X cubed here gonna cancel that. Perfect. This is what we want. And then now you can cancel x cubed, and then you get 1/2, right? Because 2 and 4 cancel, you get 1/2. And then you're gonna get just integrate cosine u du. Now you can integrate it because you know how to integrate cosine. Now it's easy to integrate. The process that I just did here, this is called the substitution rule. That is going to be our basic technique for integration. We're gonna ask you a lot to do the substitution rule. So this is required for calculus 1. So for the next 5 or 6 example, we're gonna practice on the substitution rule. And the idea is as I just shown on this slide. So what I am going to do is we are going to change the variable from x to u. So our integrand is much simpler. And then I can integrate it easily. All right, so I know 3:50 now, so we have about 25 minutes left. So we are going to go over some examples now. So any questions so far? Sounds good. No questions? All right. So, well, I think, let me see. We have 6 example lined up for today. All right. So let's do that. So first, example 59. Example 59. So I want to compute the following integrals. So those are easy one. So this is start from the easy one. We're gonna just start from easy one to the medium one and then the hard one. So let's start from the easy one first. I want to integrate 4x minus 3 raised to the 24th power. Here, well, for sure, we should not expand it. Because we can, but we should not expand it. Because if you expand it, so you're gonna get 4x cubed to the 24th power, right? So you're gonna get 24, choose 0, and then 4x to the 0, 24th first, I guess, and then negative 3 to the 0, and then 24th, choose 1, 4x to the 23rd power, and then negative 1, 1, and then plus dot, 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 dot. You're gonna have so many terms, which is not preferable for this question. But here we can just pick u to be something inside parentheses, right? Once you pick u equal to 4x minus 3, what happened? So du gonna be 4dx, right? Can you follow me? Du equal to 4dx because I differentiate u with respect to x, I get 4, right? For those of you who cannot follow, think we have du over dx here, so you get 4, which is similar to du equal to 4dx, which is similar to dx equal to du over 4. So when I integrate, I'm going to say integrate 4x minus 3 to the 24th power dx. So I'm going to switch my 4x minus 3 to u. And then we're going to switch dx to du over 4. Make sense? This going to shift to u. This going to shift to that. If you are a beginner, I would recommend you to write everything. If you go too fast, you may get lost easily. So here, I get a quarter time integrate u to the 24th power du. This is a quarter time u to the 25th over 25th, right? And then plus c. And then the last step is you need to get back your original variable. So now I have 1 over 100 times u, which is for x minus 3 to the 25th power, and then plus c. So at the last step here, I replace u by for x minus 3, the one that I use the substitution. Make sense? So this is considered as a simple one. So as I told you, as a beginner, I would recommend you to write everything. But after midterm, when you feel like, hey, Ajahn, I'm more comfortable with substitution, you can go faster. Yes, at that time, I want you to go faster at that time after midterm. But before midterm, please go slow, because if you make a mistake, so I know this is your mistake. All right, so next, I am going to do this question. Yeah, when you look at the question for the first time, you can see that I have secant and tangent together. So in my head, hey, Ajahn, I have the formula secant tangent equal to secant plus c, right? Well, I have this formula. I want to use this formula so bad, right? Because it looked like we can use this formula, but we just need to simplify a little bit so the form match with the one that we have. So I'm going to pick u to be x squared. So once you pick u to be x squared, so my du going to be 2x dx, right? Because you differentiate x squared with respect to x, and then you're going to get dx equal to du over 2x. I'm trying to go slow here. And then after that, I integrate x times secant x squared tan square x dx. This is just the question. So I am going to say x squared is my u, right? Tan x squared is my u. And my dx is going to be du over 2x. All right. X cancel. Sounds good. And then I have 1/2 integrate secant u tangent u du. Sweet, right? This is 1/2 times secant u plus c. And that will be 1/2 secant x squared plus c. This is your answer. Simple like that. Does it make sense? This is how we use the substitution rule. So those two questions are easy. So as I told you, I'm going to show you the medium question and the hard question as well. So let's go further. So I'm not going to give you a break because I think we should keep going, and then maybe we're going to leave 5 to 10 minutes early. All right. So next we look at example 60. All right. Example 60, I want to integrate this thing. So tell me in the chat, what formula do you want to use if you see question 60.1? What formula do you want to use when you see this 1 over square root 1 minus 9x square root on the denominator? Kittipat say arc sine. So Priyadon say arc sine. Do you agree, everyone? Arc sine seems pretty sweet, right? Because for the formula, we have integrate 1 over square root 1 minus x squared dx. Well, this is arc sine. So I expect that my answer gonna be in terms of arc sine. However, I have 9x squared here. Somehow I need to adjust my integrand so I can match with my formula. So that is not hard. So I'm gonna just say this is integrate square root 1 over square root 1 minus 3x in parentheses square. The reason why I do this because at the end what I want 1 over square root 1 minus u square du, right? So I can get arc sine u. That is my goal. So I'm trying to do that. So I simplify my 9x squared to 3x in parentheses square. Well, because I want that form, so I'm gonna let my u to be 3x. That means my du gonna be 3dx. That means my dx gonna be du over 3. Well, better. All right, so here I'm gonna say this is my integrate 1 over square root 1 minus u square du over 3, right? Because I switch my dx to du over 3. And then here we go. Now I pull out my 1/3. So I have integrate 1 over square root 1 minus u square du. So that means I get 1/3 times arc sine u plus c, right? And then, well, that means 1/3 times arc sine 3x plus c. All right, done. This is still easy. Well, a little bit almost medium, but still easy one. All right, so 60.2. I want to integrate sine x plus cosine x in parentheses square. Well, again, I am going to expand it. So I have sine x, sine square x plus 2 times sine x cosine x. Expand it. You see what happened? So after you expand it, I have sine square and cosine square. So group it together. So this is 1, right? It is 1 because we use trigonometric identity. So we know that sine square plus cosine square equal to 1. And then after that, well, I have to integrate sine x cosine x dx and then plus integrate 1 dx. So this term, I'm happy with it, right? The only term I need to simplify more is the first term. I have sine and cosine together. So what should I do? What should I do? Sine and cosine together. So for sure, we don't have the product rule, right? And we know how to integrate sine. We know how to integrate cos. We just learned how to do the substitution rule. So for this question, well, I'm gonna let you to be sine x. Just try it. So my du gonna be cosine x dx, right? And then that's mean by dx is going to be du over cosine x. Well, I try it. And then I hope it worked well on my question here. So I'm gonna switch my sine x to u. This is cosine x. Dx is going to be du over cosine x. Bam! This is good, right? And then I just keep that. I'm gonna integrate all at once on the last step. So this is this cancel out. So cosine cancel out. So I have integrate u du, right? So I get 2 times u square over 2. And then plus integrate 1, so I get x. So my answer gonna be u square, which is cosine, sorry, not cosine, sine square x plus c. Well, this is the answer for this question. Is that hard? No, right? I hope you find that those question example 59 and 60, those are easy one. So some of you gonna ask me that Ajahn, can I choose different u? Some of you gonna say, Ajahn, what if I pick u to be cosine x, and then my du gonna be negative sine x dx, and then my dx gonna be du over negative sine x. Can I do that? The answer is yes. Well, for one question, you can pick different u, but the answer must be the same. So for any u that you pick, if you simplify it correctly, so it's gonna give you the same, it will give you the same answer. If you pick cosine x, you can try it at home. You're gonna see that you can integrate this thing as well. And then your answer gonna be y. Sorry, your answer not your answer. If you pick your integration to be, you pick your u to be cosine. So your answer gonna be negative cosine square x plus c. Well, this answer is a correct answer too. So both of them are correct because, well, you know, sine square equal to 1 minus cosine square x. So that means you can switch these two answers back and forth. They are the same answer because we have arbitrary constancy. Does it make sense? So when you do the examples, exam or homework, and you check the answer with your friends, and you get different answers, it is possible that both of you are both correct. So don't freak out that, hey, Ajahn, my answer is not the same with my friend. It is possible that your answer gonna be correct, both of you. But it's just different form because you have arbitrary constancy. Does it make sense? All right. Uh, well, we're gonna move you to the medium one. So this is the medium one on the exam. So hopefully we can do one hard question today, but so let's look at the medium one. So I want to integrate x square root to x minus 1 dx. All right. How do you do with this question? So first of all, I'm going to pick my u. Well, what should I pick for u here? So I am going to pick u to be something under square root, right? And I hope that I am going to get something that can cancel out. So I'm going to pick u to be 2x minus 1. All right, try it. So my du going to be 2 dx, right? Because I differentiate 2x minus 1, I get 2. And then my dx going to be du over 2. Okay, let's do it. Let's do it. Hopefully we get something nice. Integrate x square root u dx. Change the x to du over 2. And that is 1/2 integrate x square root du, or square root u du. Some of you gonna say, Ajahn, I'm crying. I cannot cancel out x here. And then you just, Ajahn, I get stuck here. Done. I mean, I give up. Right? No. So don't give up. So look at the trick here. Even you cannot cancel out your x, but look at the substitution you have. You have u equal to 2x minus 1. Can you simplify x into something in terms of u? So from here, you're going to have u plus 1 equal to 2x. You're going to have x equal to u plus 1 over 2. Not bad. So I am going to simplify that x to u plus 1 over 2. And then multiply square root u du. So now everything is in terms of u now. So even you cannot cancel x, but you can simplify x in terms of u. You should do it. And then I just did it here. So I simplify x to u plus 1 over 2 because my substitution is not that hard. So I can simplify x to u. And then after that, let's see what happens. So I pull out 2, so I get a quarter. So I have integrate. So what if I want to integrate u plus 1 times square root u? Well, why don't we expand it and integrate, right? So let's do it. So I'm gonna switch my u square root u to the 1/2 du. And then now I expand it, so I get a quarter time integrate u to the uh, 3/2 plus u to the 1/2 du. I don't like to keep my square root. I love to express it as u to the negative u to the 1/2, because I know that most students gonna be more comfortable when you see u to the n, because you know how to integrate this thing, right? To be u to the n plus 1 over n plus 1. We are comfortable to see this form. So that's why I say, hey, when you see square root u, I switch it to u to the 1/2 first, because it's gonna make us easier to integrate. So now I expand that thing so I can integrate. So I get a quarter. So integrate u to the 3/2. So I get u to the 5/2 over 5/2. So you add 1. That means here I'm gonna get that because I add 1. And then plus c. Right? Don't forget to plus c, because this is just indefinite integrals. And then here my answer is a quarter times my u is going to be 2x minus 1, 5/2 over 5/2 here, and then plus 2x plus 1, 3/2 over 3/2 plus c here. I'm done with this question. If you are not comfortable to simplify, leave it there. Don't simplify. You know, this answer is acceptable. If you simplify it, and I told you already, if you simplify it and your simplification is wrong, you lose your point. So to be safe, I'm not going to simplify it, right? Well, I want full credit. Well, I am not going to simplify it. I just leave it there. I'm done because my answer is correct now. I solve everything. All right, so let's do another example. So let's do another medium one. All right, 62. All right, maybe this is the last one for today, I think. Yeah, this is the last one for today, because 63 and 64 are the medium to hard one. Maybe we're gonna continue that on next Monday. And then, well, we're gonna start definite integral next time. So let's look at another medium one, the last one for today. So we have integral of x to the 14 power times x to the 5th power plus 1 to the 1/3 dx. So how do I deal with this thing? So what is my u here? So type in the chat, please. What is going to be your choice for your u? Is it trivial, obvious? You with me? What do you think? What is going to be my u here? Are you, everyone is with me? Okay. Well, for those of you who answer, I pray for you. So you're gonna get A from me. I pray for you. Thank you, Kitipat, Chuin, Turadi, Ganpot, and Gorika. So we are going to choose you to be x to the 5th plus 1, right? Well, it's pretty obvious to my side. Well, so from that, I am going to have du over dx to be 5x to the 4th power, and that means dx is going to be du over 5 to the 5x to the 4th power. All right, so I integrate that. So I have x to the 14 power, and then x to the 5th power plus 1 to the 1/3 dx. What else? Oh, this is just a question. So I am going to use my substitution. So this is my u, and then I'm gonna replace the x by du over 5x to the 4th power. And then after that, x to the 4th power cancel a little bit, right? So you have x to the 10 power left. So you have integrate x to the 10 u to the 1/3 du. What else? So you can see that you have x to the 10 power left. So you have to simplify it to something in terms of u, right? Something in terms of u. So because you know that u equal to x to the 5th power plus 1. So x to the 5th power equal to u minus 1. Okay, that means x to the 10 power, this is u minus 1 square, right? And that means x to the 10 power, this is u square minus 2u plus 1. Not bad. So I'm gonna get this thing back to u square minus 2u minus 1, plus 1, u to the 1/3 du, right? And then now I can simplify that. So, well, go slow. So I'm gonna get integrate u to the 7/4 minus 2u to the 4/3. Oh, sorry, that's 7/3. 7/3 minus 2u to the 4/3 plus u to the 1/3 du, right? And then after that, I integrate that. So I'm gonna, I think I forgot something. I forgot 1/5, right? From that. So I have 1/5. That is from the my chain of variable substitution. And then that is 1/5. And then I integrate u to the 7/3. So I get u to the 10/3. All right. And that is u to the 7/3. And then u to the 4/3. And then plus c. Sounds good, right? And then that is my answer gonna be 1/5 times x to the 5th power. Oh, you have to switch it back to x to get full credit. Well, but to simplify, if you don't want to, fine. Well, unless the question says simplify it. But if you don't, if the question didn't say anything, you are fine to leave it there. So, all right, good. All right, this is my answer for this question. 62, not that hard, right? Better? All right, so next time we are going to look at question 63 and 64. You can try it at home first. And then when we come back next Monday, so we're gonna look at those two questions, which consider to be the medium to hard one. But before we go, so let's talk a little bit more. I beg you for 1 or 2 minutes. So this is for beginners. Well, when you integrate, let's say if I want you to integrate x times sine x squared plus 1. For example, this, for beginners, I would recommend you to say, hey, Ajahn, I'm going to let u to be x squared plus 1. And then I have du equal to 2x dx. And then you go from there. So you switch it to be x and then sine u and then du over 2x. This is for beginner. But if you feel like you are not beginner, you feel like you can do more. I mean, you feel like this is too slow for you. I want to do something faster. So what you can do is, well, I am going to tell you this thing because some student gonna say, if I like something like this, integrate x sine x squared plus 1. And then you just switch the x here. Look, you want to see the x here. Ajahn, can I say this is dx squared plus 1? And then I say over 2x here. You didn't touch u at all. So you just, hey, I'm going to choose u inside my mind. So I'm going to say my u is x squared plus 1, but I just change my substitution very fast to be dx equal to dx squared plus 1 over 2x. Is this acceptable? The answer is yes. You can. And then you can cancel out this. So you get 1/2 integrate sine x squared plus 1 dx squared plus 1. So you get negative cosine x squared plus 1 plus c, and then done. So if you feel like the one that I wrote in green, wrote in red is too slow, you can step up your solution to the blue one. The blue one is the one that is acceptable for the exam too. If you write a solution as the blue one, fine, you still get full credit. But for beginners, I would recommend you to do the red one, because you are not sharp enough to just go fast, something like that. But once you do it again and again and again, you're gonna feel like, hey, if you pick your u all the time, it's gonna be too slow. So after midterm, when we do integration, we're gonna just do like I just wrote in blue. So this is the faster one, and it is acceptable for this class. All right, it's 4:20 now. So any questions? If not, I am going to end the lecture here. So any question, everyone? Any question or anything? Do you want just to give you a reminder, the homework is due this Friday, so you need to submit by noon. So be sure to complete that. Do you want me to go over the homework before we leave? Fine. No, right? Well, I think some of you already did it, so fine. So, well, we have a question from Turidi, example 62, so you can go ahead and ask it. Number 62 here. So if you don't have any question, you can leave now. But if you want to stay for question, well, stay for question. All right, thank you everyone for staying for the whole lecture. But Turidi, you can ask question,ครับ. You want to open the microphone or something?
Teacher, where is the negative sign?
Where is the...
In the three
no.
line. In the third line. In the third line.
Okay. My bad. I need negative sign here, right? Is that what you mean?
Yes.
Okay. My bad. I did it too fast. So this must be negative sign. Good. Fix it. Negative sign. All right. Thank you.
Teacher,
two. Sorry, two.
The two. Where's the two?
Okay.
Thank you, teacher.
Okay, thank you. I did it too fast. Yeah, we have negative 2 here too. All right, sounds good. All right, hope you have a good evening.
So we cannot pull it out, right?
You can if you want, but I'm going to leave it there. If you want to simplify, I can simplify as well. So, well, let's simplify it because seem like you want to simplify it. So, okay, so if you want to simplify it, this is just for those of you who want to simplify. So you can get 3 over 50, right? Because you have 10 over 3 here. So you get 3 over 50 x to the 5th power plus 1 to the 10 over 3. And then minus, that will be 6 over 35 x to the 5th power plus 1, 7 over 3. And then plus 3 over 20 x to the 5th power plus 1 to the 4 over 3. And then plus c. Yes. Well, it is a little bit risky to simplify because sometimes you forgot your constant or something, but this is your answer. All right, thank you everyone. And then if you have any question, let me know. So we're done for today. So next week we're gonna do more hard examples. All right, thank you.
I have question.
Okay, go for it.
Can you open the slide number 8?
8. Okay, go.
Yes.
All right. Okay. Here,
Oh, sorry, number 9.
9.
Yes, yes. This page.
Oh, this one.
No.
Oh, 8, 8. Okay, this one. Okay.
No, next page. Sorry.
9. Okay, this.
I confused the coefficient 2 in
The
the
green
line
one.
2. No, in the black one.
Oh, okay. What happened?
In the line 2, line 2 to the line 3. I confused that how number 2 is in front of the integration.
Oh, okay. I think what you forgot is this line to this line, right?
Yes.
Okay. So I have, well, from here, I can express this thing as integrate secant square x dx minus integrate 1 dx. Good. And then now I group that, the one that I highlight in orange, and that together. So that's, I have that. Feel better?
Oh, okay.
I group that and that together, so I get that.
Oh, thank you.
That's why I have coefficient 2 here. So you can see that I dropped my last term because I group it up with the first one.
Oh, okay.
Good. All right.
Yes.
Anything else?
No.
All right. Thank you, Tan Pon, right? Okay. Thank you. All right. Okay. So let me know if you have any question in the chat or email. All right. So hope everyone have a good evening. All right. Happy September 9.